particles are incredibly sparse, with an average density of about 1 atom per cubic meter. This makes the vacuum of space vastly less dense than any vacuum achieved on Earth. Even in the most empty regions, such as the so-called voids between galaxies, the vacuum is still not a complete nothingness. Quantum mechanics introduces another fascinating aspect to the idea of vacuum. According to the theory of quantum fluctuations, even in a perfect vacuum, energy is not zero. Instead, it fluctuates in what is called vacuum energy. This energy arises due to the constant creation and annihilation of particle-antiparticle pairs that occur spontaneously in empty space. These fluctuations are a direct result of the Heisenberg uncertainty principle, which states that the exact energy of a system cannot be determined with absolute precision at all times. This means that even in the absence of observable matter, the vacuum still contains a certain amount of energy. The concept of vacuum energy is crucial to understanding phenomena such as dark energy, which is believed to be responsible for the accelerated expansion of the universe. Though not yet fully understood, dark energy is theorized to interact with the vacuum on a cosmological scale, influencing the dynamics of galaxies and the overall structure of the universe. The search for a deeper understanding of the true nature of vacuum and its energy continues to be a major area of research in cosmology and theoretical physics. Furthermore, the vacuum of space is not entirely devoid of fields. Electromagnetic fields, gravitational fields, and even more exotic fields like scalar fields exist throughout space, filling the so-called vacuum with dynamic interactions. These fields influence the behavior of matter and energy in space, and their interactions can lead to phenomena such as the bending of light around massive objects, known as gravitational lensing. One of the most surprising aspects of the cosmic vacuum is its role in the transmission of light and other forms of electromagnetic radiation. While the vacuum does not impede the movement of light, it can still influence the behavior of photons. For example, the vacuum can cause a phenomenon called vacuum polarization, in which virtual particle-antiparticle pairs temporarily appear and disappear in the presence of an electromagnetic field. This effect can alter the properties of light as it travels through space, potentially leading to observable phenomena like the change in the polarization of light from distant stars. Additionally, the vacuum of space plays a critical role in the concept of the cosmological constant, introduced by Albert Einstein in his theory of general relativity. The cosmological constant was originally proposed as a term to balance the equations of relativity and maintain a static universe. After the discovery of the universe's expansion, the cosmological constant was abandoned by Einstein, but it has since been resurrected in the context of dark energy. This term essentially represents the energy density of the vacuum, contributing to the accelerated expansion of the universe. In terms of human exploration and technological advancements, the concept of vacuum has practical implications. Spacecraft and satellites are designed to function in a vacuum, which presents unique challenges in terms of thermal regulation, radiation shielding, and propulsion. The absence of atmospheric pressure means that heat cannot be transferred by conduction or convection, requiring spacecraft to rely solely on radiation for temperature control. Additionally, vacuum conditions in space can lead to the outgassing of materials and the erosion of surfaces exposed to the harsh environment. In laboratory settings, scientists have been able to create near-perfect vacuums, where the density of particles is extremely low, but achieving a complete void remains impossible. Modern techniques, such as using magnetic fields to trap particles or employing ultra-cold temperatures to slow the movement of particles, have allowed researchers to study the properties of vacuums and simulate conditions similar to those found in deep space. Despite all the advancements in understanding the vacuum of space, many questions remain. For example, scientists are still trying to understand the relationship between vacuum energy and the expansion of the universe. Some theories suggest that the vacuum could play a key role in the creation of the universe itself, possibly even giving rise to the Big Bang. Others speculate that the nature of vacuum energy could provide answers to some of the most profound questions in physics, such as the nature of dark matter and the fate of the universe. Thus, the cosmic vacuum is not a simple, empty void but rather a dynamic, complex entity with its own set of properties and behaviors. The exploration of this enigmatic aspect of the universe continues to be a key focus of modern physics, with implications for everything from the evolution of the cosmos to the fundamental laws that govern matter and energy. As our understanding deepens, the cosmic vacuum may reveal even more secrets about the universe and our place within it. As we continue to delve into the mysteries of the cosmic vacuum, it is important to consider the potential impact of these discoveries on our broader understanding of the universe. The study of vacuum energy and its relationship with the expansion of the universe could offer profound insights into the fate of the cosmos. For instance, some cosmological models suggest that the energy inherent in the vacuum could be driving the universe toward a state of accelerated expansion, potentially leading to a Big Rip, in which galaxies, stars, and even atoms are eventually torn apart by the growing vacuum energy. Furthermore, understanding the nature of cosmic vacuum fluctuations could offer a better understanding of the early moments of the universe, specifically during the period of cosmic inflation. Inflationary theory proposes that the universe underwent an incredibly rapid expansion in the first few moments after the Big Bang, stretching from subatomic scales to macroscopic dimensions. This theory not only explains the large-scale uniformity of the universe but also suggests that quantum fluctuations in the vacuum could have played a role in shaping the formation of the first structures in the universe, such as galaxies and clusters of galaxies. The discovery of vacuum energy's role in cosmic inflation also brings up another important consideration: the potential for the vacuum to transition between different states or phases. This phenomenon, known as a vacuum phase transition, could have far-reaching consequences for the nature of space and time itself. It is hypothesized that such a transition might have occurred in the early universe, triggering the rapid expansion and shaping the large-scale structure we observe today. Some theories even suggest that vacuum phase transitions could occur again in the future, leading to dramatic changes in the behavior of the universe. Moreover, the concept of vacuum energy extends beyond just cosmology and theoretical physics. It also has potential applications in cutting-edge technologies. For example, vacuum fluctuations are thought to play a role in the Casimir effect, a phenomenon in which two closely spaced conducting plates experience an attractive force due to the vacuum energy between them. This effect is not just a curiosity of theoretical physics but has practical implications in the field of nanotechnology, where understanding and manipulating vacuum forces could lead to the development of new materials and devices. In the field of quantum field theory, the vacuum is not simply the absence of particles but is understood as the lowest energy state of a quantum field. This view leads to the notion of virtual particles, which are particle-antiparticle pairs that constantly pop in and out of existence, even in a perfect vacuum. While these virtual particles cannot be directly observed, their presence has been inferred through indirect measurements and phenomena such as the aforementioned Casimir effect. The study of these virtual particles and the fluctuations they generate provides deep insights into the fundamental nature of reality. In addition to quantum fluctuations and vacuum energy, another fascinating aspect of the cosmic vacuum is its role in the propagation of gravitational waves. Gravitational waves, which are ripples in spacetime caused by accelerating massive objects, travel through the vacuum of space at the speed of light. The detection of these waves, first achieved in 2015 by the LIGO experiment, opened a new era in astrophysics, allowing scientists to observe distant cosmic events such as merging black holes and neutron stars. The ability of gravitational waves to propagate through the vacuum without losing energy provides crucial information about the properties of space and time, as well as the dynamics of massive astrophysical systems. The study of cosmic vacuum also raises fundamental philosophical questions about the nature of emptiness and existence. Is the vacuum truly empty, or is it filled with subtle, hidden properties that we have yet to understand fully? If the vacuum is not a true void but rather a dynamic, fluctuating field of energy, what does this imply about the concept of nothingness? Could the vacuum itself give rise to new forms of matter or energy, potentially leading to discoveries beyond our current comprehension? Finally, as our understanding of the cosmic vacuum continues to evolve, so too does our approach to exploring the universe. Space exploration missions, both manned and unmanned, are designed to probe the vacuum of space and study its properties directly. Instruments aboard spacecraft such as the James Webb Space Telescope, the Voyager probes, and the upcoming LISA, Laser Interferometer Space Antenna, mission aim to provide new insights into the nature of the cosmic vacuum, including the detection of gravitational waves, the observation of distant galaxies, and the study of dark energy. The study of the cosmic vacuum, its energy, and its role in the evolution of the universe represents a crucial frontier in scientific research. By continuing to investigate these phenomena, physicists and cosmologists hope to unravel some of the deepest mysteries of the universe, from the origin of the cosmos to the fate of its ultimate evolution. The quest to understand the true nature of space, time, and vacuum energy may one day provide the key to unlocking the most profound questions in science, philosophy, and even our understanding of existence itself. As we venture deeper into the study of cosmic vacuum, we must also consider the potential applications and technologies that could emerge from this understanding. The exploration of vacuum energy and quantum fluctuations could lead to breakthroughs in a variety of fields, from energy generation to quantum computing. For example, if we could harness vacuum energy, it might provide a novel source of power. Though this idea remains speculative, the concept of zero-point energy, the energy that exists in empty space, has long intrigued scientists. If methods for extracting or tapping into this energy could be developed, it might provide humanity with an almost limitless, clean source of power. However, much more research would be needed before such technologies could be realized. In quantum computing, the understanding of vacuum states and quantum fields is central to the development of quantum algorithms and quantum bits, qubits. Quantum computers rely on the principles of superposition and entanglement, and the vacuum's behavior at the quantum level plays a role in these phenomena. By understanding how particles interact in a vacuum and how vacuum fluctuations influence quantum systems, scientists could potentially create more efficient and powerful quantum computers. These machines could revolutionize fields such as cryptography, material science, and complex system modeling. Another area where the study of vacuum energy could have significant implications is in the field of high-energy physics, particularly in particle accelerators. Understanding the properties of the vacuum is crucial for experiments that explore the fundamental particles and forces of nature. The Large Hadron Collider, LHC, for example, seeks to probe the deepest mysteries of the universe, including the Higgs boson and other elementary particles. In these experiments, scientists study the interaction between particles in near-vacuum conditions, helping to reveal the forces and particles that govern the behavior of matter. The more we understand the nature of the vacuum in these environments, the more accurately we can model particle interactions and gain insight into the laws of physics. The concept of the vacuum also plays a crucial role in the search for dark matter and dark energy, two of the most elusive and enigmatic components of the universe. Dark matter, which makes up roughly 27% of the universe, is believed to interact with regular matter through gravity but not via electromagnetic forces, making it invisible and difficult to detect. The vacuum could hold clues to the nature of dark matter, especially in the way it might interact with quantum fields and energy fluctuations. Similarly, dark energy, which is thought to be responsible for the accelerated expansion of the universe, may be closely related to the properties of the vacuum. Researchers are investigating the link between vacuum fluctuations and the mysterious force of dark energy, hoping to uncover how it influences the dynamics of the cosmos on a grand scale. In the realm of astrophysics, the cosmic vacuum offers a unique vantage point for studying phenomena like black holes and neutron stars. These extreme objects have powerful gravitational fields that warp spacetime itself, affecting the vacuum around them. For instance, near a black hole, the vacuum undergoes significant alterations, including changes in the way light and matter behave. The study of how vacuum energy behaves in the vicinity of such objects can help scientists understand the properties of these exotic environments and even shed light on the nature of spacetime singularities. Additionally, phenomena like Hawking radiation, which is theorized to arise from quantum effects near black holes, may further illuminate the relationship between vacuum fluctuations and the behavior of these massive objects. The study of vacuum also raises the possibility of discovering new forms of matter and energy that lie beyond our current understanding. For example, some theories suggest that the vacuum could give rise to strange and exotic states of matter, such as vacuum condensates or quark-gluon plasma. These states of matter, which occur at extremely high energies, may offer new insights into the early universe and the conditions that prevailed shortly after the Big Bang. Exploring the properties of the vacuum could also provide a deeper understanding of how the fundamental forces of nature, gravity, electromagnetism, the strong force, and the weak force, are interrelated and may ultimately unify into a single, cohesive theory. On a more speculative note, some theories in physics suggest that the vacuum may be a gateway to alternate dimensions or parallel universes. This idea is inspired by the concept of the multiverse, where the vacuum could be a dynamic medium that connects different regions of spacetime, potentially allowing for the existence of other universes. While such theories remain speculative and untested, the exploration of the cosmic vacuum could eventually lead to breakthroughs that challenge our understanding of reality itself. Finally, the study of the cosmic vacuum challenges our philosophical and metaphysical views on the nature of nothingness, existence, and the origins of the universe. If the vacuum is not empty but filled with energy, fields, and quantum fluctuations, what does this mean for our concept of nothingness? Philosophers have long pondered the idea of the void and what it means for something to come from nothing. In light of modern physics, the vacuum challenges traditional notions of creation and existence, offering a more nuanced understanding of the universe's origins. The study of the cosmic vacuum, therefore, not only contributes to our scientific knowledge but also invites us to reconsider our fundamental assumptions about reality, existence, and the nature of the cosmos. In conclusion, the cosmic vacuum is far from a simple void. It is a dynamic, complex environment filled with quantum fluctuations, vacuum energy, and fields that influence the behavior of matter and energy across the universe. The study of the vacuum has far-reaching implications for many areas of science, from cosmology to quantum mechanics, and may eventually unlock new technologies and a deeper understanding of the nature of reality itself. As we continue to probe the mysteries of the vacuum, we may uncover answers to some of the most profound questions in science and philosophy, ultimately revealing new insights into the very fabric of the universe. As we look forward to further advancements in the study of the cosmic vacuum, it's essential to consider the growing role of experimental methods and future technologies in advancing our understanding. The future of space exploration and theoretical physics hinges on our ability to refine our observational tools and develop novel techniques for studying the vacuum on both macroscopic and microscopic scales. One of the most promising developments in the field is the potential of advanced space telescopes, such as the James Webb Space Telescope, JWST, to deepen our understanding of the vacuum. The JWST, designed to observe the universe in infrared wavelengths, could provide new insights into the cosmic microwave background radiation, the faint echo of the Big Bang, and the subtle fluctuations of the vacuum in the early universe. By investigating distant galaxies and the regions between them, the telescope could help researchers study how vacuum energy and dark energy influence the structure and expansion of the universe on a large scale. These observations will be crucial for refining our models of cosmology, particularly in understanding the role of vacuum energy in accelerating the expansion of the universe. In addition to astronomical observations, the development of more sensitive detectors and particle accelerators will play a key role in exploring the properties of vacuum. The next-generation particle accelerators, such as the proposed Future Circular Collider, FCC, or the International Linear Collider, ILC, aim to probe even higher energy scales than current facilities like the LHC. These experiments will provide deeper insights into quantum fields and vacuum fluctuations, helping to explore phenomena such as the Higgs field and its role in giving particles mass. The more we learn about the behavior of fields in a vacuum, the closer we get to understanding the fundamental forces and particles that govern the universe. On Earth, laboratory experiments are also crucial in simulating and studying vacuum conditions. One of the most significant methods for investigating the properties of vacuum is through ultra-high vacuum chambers, which allows scientists to simulate near-perfect vacuum conditions. These chambers are used in a variety of fields, including material science, nanotechnology, and fundamental physics. Through these experiments, scientists can observe how materials behave in extremely low-pressure environments, how particles interact with one another, and how energy is transferred in the vacuum. Further advances in vacuum technology could open new frontiers in our understanding of quantum mechanics and material properties. Another exciting avenue of research lies in the realm of quantum optics and the manipulation of vacuum states in laboratory settings. Quantum optics explores the interaction between light and matter at the quantum level, and researchers are developing techniques to control and manipulate the quantum vacuum in novel ways. One such approach involves the use of vacuum cavities to trap light or manipulate electromagnetic fields within a confined space. This technology could lead to the creation of highly sensitive detectors for gravitational waves, dark matter, and other elusive phenomena. Moreover, The ability to control the quantum vacuum could open new possibilities for quantum communication and quantum networks, which are expected to revolutionize information technology in the coming decades. The study of the cosmic vacuum also intersects with the development of cutting-edge concepts like quantum gravity, a theory that aims to reconcile general relativity and quantum mechanics. The nature of vacuum plays a critical role in these efforts, as quantum fluctuations and vacuum energy are believed to be fundamental to the structure of spacetime itself. Researchers working on theories of quantum gravity, such as string theory or loop quantum gravity, propose that the vacuum may not be a simple, static backdrop to the universe, but a dynamic and malleable entity that shapes the very fabric of spacetime. These theories suggest that the vacuum could contain exotic states or phenomena, such as higher-dimensional spaces, that have profound implications for our understanding of the universe at both the smallest and largest scales. In the field of cosmology, the study of vacuum fluctuations is central to understanding the early moments of the universe. Quantum fluctuations in the vacuum during the first fractions of a second after the Big Bang could have had a profound impact on the formation of the universe's large-scale structure. These fluctuations are thought to have seeded the formation of galaxies, stars, and clusters of galaxies, influencing the distribution of matter across the universe. Future advancements in both observational techniques and theoretical models will likely provide more detailed insights into how these early vacuum fluctuations shaped the universe's evolution. Furthermore, as we investigate the nature of the vacuum on cosmological scales, we must also explore the role of the vacuum in phenomena like cosmic inflation. Inflationary theory posits that the universe underwent a rapid exponential expansion in the first moments after the Big Bang, driven by vacuum energy. The study of how vacuum energy behaves during inflation could help explain the uniformity of the universe and the existence of cosmic structures. It could also shed light on the nature of the multiverse hypothesis, which proposes the existence of multiple universes, each with its own set of physical laws. While the idea of a multiverse is speculative, ongoing research into vacuum dynamics could provide the theoretical foundation for exploring such possibilities. The cosmic vacuum also has implications for the study of extreme cosmic events, such as gamma-ray bursts, supernovae, and the merging of black holes and neutron stars. These events release vast amounts of energy and influence the surrounding vacuum. For example, the gravitational waves detected by LIGO and Virgo collaborations have provided direct evidence of the effects of extreme vacuum fluctuations in the presence of massive objects. As we continue to observe and analyze such events, we can gain a deeper understanding of how the vacuum behaves in the vicinity of extremely high-energy phenomena and how these events influence the fabric of spacetime. The study of the cosmic vacuum is not only essential for advancing our knowledge of the universe but also for addressing some of the deepest questions in physics and philosophy. By understanding the nature of vacuum energy, quantum fluctuations, and the relationship between space and time, we may be able to answer fundamental questions about the origin of the universe, the nature of dark matter and dark energy, and the ultimate fate of the cosmos. Furthermore, the exploration of vacuum could provide new insights into the relationship between quantum mechanics and gravity, potentially leading to a unified theory of physics that explains all the fundamental forces of nature. As we continue to probe the mysteries of the cosmic vacuum, we are also reminded of the profound interconnectedness of the universe. The study of vacuum is not merely an academic exercise, but a journey that could unlock new technologies, new understandings of the cosmos, and perhaps even new ways of thinking about our place in the universe. Whether it is through the development of advanced theoretical models, the detection of new phenomena, or the creation of innovative technologies, the exploration of the cosmic vacuum will continue to be at the forefront of scientific discovery for generations to come. As we move forward in our exploration of the cosmic vacuum, it is crucial to address the potential philosophical and metaphysical ramifications of our discoveries. The deeper we delve into the nature of nothingness, the more we realize how much of our understanding of the universe is influenced by concepts that were once considered purely abstract or speculative. The quantum vacuum, with its unpredictable fluctuations, challenges traditional ideas of a void and forces us to reconsider what it means for space to be truly empty. For centuries, scientists and philosophers have debated the nature of the void, with classical physics assuming a vacuum as an empty space devoid of matter and energy. However, as quantum mechanics and relativity have revealed, the vacuum is far from empty. Instead, it is a bustling field of activity, a dynamic environment where particles appear and disappear, and where energy fluctuates even in the absence of matter. This revelation forces us to rethink fundamental philosophical questions about existence, nothingness, and the origin of the cosmos. This new understanding of the vacuum also calls into question the very nature of reality. If the vacuum is teeming with energy, fields, and quantum fluctuations, does this imply that all of space is inherently alive in some sense, constantly in a state of potentiality? Could this understanding of the vacuum provide a clue as to how the universe itself emerged from an initial singularity? Some theories suggest that the vacuum may have played a direct role in the Big Bang, with quantum fluctuations in the vacuum triggering the expansion of the universe. This idea opens up intriguing possibilities about the fundamental connection between the vacuum and the birth of space and time itself. Moreover, the concept of the vacuum has profound implications for our understanding of time. In classical physics, time is typically viewed as a continuous, flowing dimension that is independent of the physical space in which events occur. However, the study of the vacuum and its relationship to quantum fields has led to the idea that time itself may be subject to quantum fluctuations. Just as particles can pop in and out of existence in a vacuum, so too might the fabric of spacetime itself be subject to similar fluctuations. This could imply that time is not a fixed, immutable backdrop to the universe but a dynamic and fluid entity that could vary on the smallest of scales. The relationship between the vacuum and spacetime also raises intriguing possibilities about the nature of the future of the universe. Some cosmological models suggest that vacuum energy may play a pivotal role in the eventual fate of the cosmos. The concept of vacuum metastability proposes that the vacuum could transition into a lower energy state, leading to dramatic changes in the laws of physics and the structure of the universe itself. Such a transition could potentially signal the end of the current universe and the beginning of a new one, a concept that aligns with certain theories of the multiverse, where universes continually evolve from one to the next. In practical terms, the discoveries related to the cosmic vacuum could lead to innovations in technology and energy generation. As our understanding of vacuum energy deepens, we may find ways to harness the energy contained within the vacuum itself. While the extraction of zero-point energy remains a speculative idea, advances in nanotechnology and quantum engineering may eventually provide the tools necessary to manipulate and exploit these vacuum energies. Such breakthroughs could usher in a new era of energy production, with vast implications for everything from powering cities to propelling spacecraft across interstellar distances. The study of vacuum also offers insights into the development of new materials with extraordinary properties. For example, materials that manipulate vacuum fluctuations could lead to innovations in computing, communications, and even medicine. The ability to control quantum states of matter, such as superposition and entanglement, has the potential to revolutionize the fields of quantum computing and communication. Scientists are already exploring ways to exploit quantum effects in materials to create faster, more efficient computers and networks that could vastly exceed the capabilities of today's technology. Additionally, the study of the cosmic vacuum is intertwined with the search for new and exotic states of matter, such as dark matter and dark energy. These mysterious components make up the majority of the universe's mass energy content, yet they remain undetected by conventional means. The vacuum may hold the key to understanding the properties of these elusive phenomena, particularly through its interaction with quantum fields. If we are able to unlock the secrets of dark matter and dark energy, we could gain profound insights into the true nature of the universe and its fundamental composition. As our understanding of the cosmic vacuum expands, so too does our recognition of its significance in the broader context of science and philosophy. The study of the vacuum is not just about exploring the void, it is about investigating the very foundation of reality itself. Whether it is through the search for new forms of energy, the exploration of quantum fields, or the quest to understand the ultimate fate of the universe, the study of the cosmic vacuum is central to unlocking the deepest mysteries of the cosmos. Moreover, the investigation of the vacuum forces us to confront some of the most profound questions about the nature of existence. What does it mean for something to exist if even empty space is filled with energy and potential? Is the universe truly a product of randomness and quantum fluctuations, or is there a deeper order and purpose that governs its structure? These are questions that extend beyond the realm of science and into the domain of philosophy, prompting us to reconsider our place in the universe and the nature of reality itself. In conclusion, the cosmic vacuum is a far richer and more complex concept than we ever imagined. It is not an empty void but a dynamic, fluctuating field that holds the key to understanding the fundamental workings of the universe. Whether it is through the study of vacuum energy, the exploration of quantum fields, or the search for new technologies, our understanding of the vacuum will continue to evolve and shape the future of science. As we push the boundaries of knowledge, we may uncover new realms of existence and new possibilities for the future of humanity. Continuing from where we left off, the study of the cosmic vacuum not only illuminates the deepest aspects of fundamental physics but also encourages us to rethink the boundaries between the physical and the philosophical. The idea that what we once considered empty space is anything but truly empty opens up exciting new vistas for science and thought. The more we learn about the vacuum, the more we realize how interconnected it is with all aspects of the universe, from the smallest subatomic particles to the largest cosmic structures. It might be tempting to think of the vacuum as something that merely serves as a backdrop for the universe, but as our understanding deepens, it becomes clear that the vacuum plays a crucial, active role in shaping the cosmos. From the way it influences quantum particles to its connection with the large-scale behavior of galaxies and the universe's expansion, the vacuum is a dynamic and essential element of the universe's fabric. As we continue to investigate the cosmic vacuum, it will be essential for scientists to adopt interdisciplinary approaches. The intersection of quantum mechanics, general relativity, and cosmology is where many of the most exciting breakthroughs are likely to occur. Physicists are already working toward a theory of quantum gravity that seeks to unify these diverse areas of study. The properties of the vacuum are central to this theory, as they influence both quantum phenomena on the smallest scales and gravitational effects on the largest scales. Ultimately, the discovery of how these forces interact within the context of the vacuum could lead to the unification of the four fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single, comprehensive theory. This theory would not only revolutionize our understanding of the universe but could also have profound practical applications, from space travel to energy production. In addition to this, advances in quantum field theory could lead to breakthroughs in our understanding of the vacuum's role in fundamental processes, such as particle creation and annihilation. The ability to manipulate quantum fields and understand the fluctuations in the vacuum could enable technologies that seem like science fiction today, such as the creation of stable wormholes for faster-than-light travel or the generation of exotic matter needed for propulsion systems like those envisioned in the concept of warp drives. While these ideas remain speculative, the study of the vacuum could provide the foundational knowledge needed to make them a reality. One of the most thrilling possibilities in the study of the cosmic vacuum is its connection to the future of space exploration. The vacuum of space itself is not just a cold, empty void, it is a region of spacetime filled with infinite possibilities for discovery. As our understanding grows, we may learn how to exploit the properties of space itself to advance humanity's ability to explore the cosmos. For instance, space propulsion technologies that leverage the manipulation of vacuum fluctuations could drastically reduce travel times to distant stars. If we can learn to exploit the vacuum for energy generation or propulsion, it could enable interstellar travel that was once considered impossible. The ability to use the vacuum as a resource could revolutionize our capacity to explore and settle other planets and even distant star systems. The potential for the vacuum to offer insight into the fundamental questions about existence and the origin of the universe remains one of its most captivating aspects. Some theories suggest that the early vacuum played a role in the Big Bang, potentially offering clues about how the universe began and whether it could have arisen from a quantum fluctuation or the vacuum itself. If this is true, it implies that the entire cosmos could be the result of an immense fluctuation of vacuum energy, an event that might have triggered the birth of space, time, and all matter. By studying these initial moments, scientists may uncover deeper insights into the conditions that allowed the universe to come into being, and whether such a creation process could happen again, possibly leading to cycles of cosmic rebirth. Moreover, as researchers delve deeper into the behavior of the vacuum, they are confronted with the possibility that our entire understanding of cosmology might need to be rewritten. The very idea of empty space could evolve into something far more complex. For instance, the so-called multiverse theory, suggesting that our universe is just one of many, each with different physical laws and properties, could be partially based on the vacuum's inherent instability and its capacity to give rise to multiple universes. This idea not only challenges our conception of the universe's uniqueness but also invites profound philosophical questions about the nature of existence itself. If the vacuum can give rise to countless universes, what does that say about the nature of reality? Are we simply one of many possible manifestations of reality, or is our universe the only one in which life and consciousness can emerge? Looking ahead, it is clear that the cosmic vacuum remains one of the most fundamental and least understood aspects of the universe. As researchers push forward with experimental and theoretical advancements, we may find that the study of the vacuum unlocks answers to some of the most profound questions in physics, cosmology, and even philosophy. Our understanding of the vacuum may ultimately reshape our entire view of the universe, offering new perspectives on time, space, matter, and energy. In terms of practical applications, the study of the vacuum holds the potential for breakthroughs in energy, computing, and materials science. As we continue to investigate the quantum properties of space, we may develop new materials with extraordinary properties, materials that could be used in everything from electronics to medical devices. Moreover, the ability to manipulate vacuum energy or quantum fields could give rise to technologies that vastly improve the efficiency of energy systems, transportation, and computing. The ultimate impact of the cosmic vacuum on our future depends not just on theoretical advancements but on our ability to translate these insights into tangible applications. Whether it's through innovations in space travel, energy generation, or material science, the discoveries surrounding the vacuum will play a central role in shaping humanity's future. In conclusion, while we have only begun to scratch the surface of understanding the true nature of the cosmic vacuum, it is clear that this is one of the most exciting and potentially transformative areas of research. The vacuum is far more than empty space. It is a dynamic, fluctuating field that holds the secrets to the deepest mysteries of the universe. As we continue to explore the vacuum's properties, we open up a new realm of possibility, one that could revolutionize our understanding of reality itself and lead to groundbreaking technologies and scientific discoveries that we can only begin to imagine. As we continue to push the frontiers of understanding the cosmic vacuum, it is clear that our journey is far from over. Each breakthrough brings with it new questions and new challenges, many of which could reshape not just our scientific knowledge, but our very understanding of existence. The study of the vacuum opens avenues for innovative technologies, deepens our grasp of the cosmos, and challenges the way we think about reality itself. One of the most profound impacts of exploring the cosmic vacuum is its potential to revolutionize our technological capabilities. The search for vacuum energy, though still theoretical, could one day lead to the discovery of new energy sources. Imagine a world where we can tap into the infinite potential of the vacuum to power our cities, spaceships, and machines. This could provide an unlimited, clean, and highly efficient energy source that would eliminate many of the energy challenges humanity faces today. The implications for energy sustainability are enormous. If we can harness even a fraction of the energy locked in the vacuum, it could change the course of human development, fueling the next stages of civilization. Moreover, quantum technologies tied to vacuum phenomena could fundamentally alter the way we interact with information. Quantum computing, which already promises to revolutionize fields like cryptography, materials science, and artificial intelligence, could take a major leap forward by exploiting the vacuum's quantum properties. With advances in quantum error correction and manipulation of quantum states within vacuum cavities, we could see the creation of computers and communication systems that are orders of magnitude more powerful than anything available today. These advancements could unlock new realms of problem solving, data analysis, and artificial intelligence applications, ultimately accelerating scientific discovery and improving everyday life. Another area where the study of the cosmic vacuum could bring transformative change is in the exploration of new frontiers in space. Space exploration, once limited to a handful of missions and distant dreams of interstellar travel, could be drastically accelerated through technologies inspired by the vacuum's properties. The idea of faster-than-light travel, once relegated to science fiction, might one day become a reality through theoretical concepts like the manipulation of vacuum fluctuations or warp drives. By understanding how the vacuum behaves under extreme conditions and learning to harness its energy, we could build propulsion systems that enable humanity to venture far beyond our solar system, potentially reaching distant stars or even exploring exoplanets in other galaxies. The potential for new materials, derived from the principles of vacuum physics, could have far-reaching applications in multiple fields. For instance, the ability to control quantum fields within the vacuum might lead to the development of materials with exotic properties, materials that could be used to create super-efficient conductors, advanced superconductors, or even materials with previously unheard-of mechanical properties. The future could bring about new ways to build infrastructure, from space habitats to ultra-strong construction materials for Earth. The possibilities in this realm are vast, and the technologies emerging from these studies could redefine everything from manufacturing to medicine. One area that may benefit from these advances is medicine. The manipulation of vacuum properties could lead to breakthroughs in medical diagnostics and treatments. For example, the quantum manipulation of light and matter within vacuum states could yield new methods of imaging, detecting diseases at earlier stages, and even creating non-invasive treatments using quantum principles. Nanotechnology, which often operates at the scale of individual atoms and molecules, could also benefit from understanding vacuum dynamics, leading to breakthroughs in drug delivery systems and personalized medicine. While these potential applications remain speculative at this point, they are not beyond the realm of possibility. As technology advances and our understanding of quantum physics and the vacuum grows, it is likely that many of these once far-fetched ideas will become tangible realities. Just as the exploration of space and quantum mechanics has transformed the 20th and 21st centuries, the study of the cosmic vacuum could catalyze the next wave of scientific and technological breakthroughs. Moreover, as we continue to explore the vacuum, we must also keep in mind the ethical and philosophical implications of these advances. The ability to manipulate spacetime, extract energy from the vacuum, or develop new quantum technologies brings with it profound responsibilities. How we use this newfound knowledge will shape the future of humanity. We must ensure that these technologies are developed in a way that benefits all of society and does not lead to unforeseen consequences. The quest for knowledge is important, but it must be balanced with an ethical framework that considers the potential impact on humanity and the environment. In addition to the practical applications, the study of the cosmic vacuum touches on deeper philosophical questions. The concept of a vacuum challenges our understanding of reality itself. What does it mean for space to be truly empty? If the vacuum is teeming with energy, virtual particles, and fluctuations, is there really such a thing as nothingness? This idea has implications not just for science but for our worldview as a whole. It forces us to reconsider the nature of existence, the universe, and our place in it. If everything is in constant fluctuation, does that mean everything is connected in ways we don't yet understand? Is reality itself a product of these quantum fluctuations, and if so, what does that tell us about the nature of time, space, and even consciousness? These deep questions challenge us to rethink the boundaries between science and philosophy, and between what we know and what we have yet to discover. As scientists continue to investigate the vacuum, they are not only unraveling the mysteries of the universe but also challenging the fundamental assumptions about reality itself. These explorations are not just about solving problems, they are about rethinking everything we thought we knew about the universe, from its origins to its ultimate fate. The cosmic vacuum is more than just a scientific curiosity. It is a doorway to new frontiers of knowledge, a concept that has the potential to transform our understanding of everything from the smallest particles to the largest cosmic structures. It offers insights into the nature of space, time, energy, and matter, insights that could change the course of human history. Whether through the development of new technologies, a deeper understanding of the universe, or a new philosophical worldview, the study of the cosmic vacuum holds the key to unlocking some of the most profound mysteries of existence. As we continue this journey of discovery, we can only imagine what the future will hold. With each new experiment, each new theory, we move closer to understanding the true nature of the vacuum and, in turn, the universe itself. The vacuum is not just the empty space that we once thought it was, it is the canvas on which the entire universe is painted, the medium through which the forces of nature interact, and the foundation on which everything exists. Our understanding of this cosmic void is the key to understanding the very nature of reality itself. The study of the cosmic vacuum is not just an exploration of empty space but a profound journey that reshapes our understanding of the universe and our place within it. As we venture deeper into this realm, we uncover new scientific principles that not only challenge established laws of physics but also offer revolutionary possibilities for future technologies and human progress. Each discovery in this field opens doors to advancements that could redefine everything from energy production to space exploration, pushing the boundaries of what is possible. The cosmic vacuum, rather than being a mere void, is filled with quantum fluctuations, virtual particles, and an underlying energy that governs the fundamental forces of nature. This vacuum energy could one day be harnessed to create entirely new sources of power, offering humanity an unlimited, clean energy supply. Such a breakthrough would revolutionize our approach to solving the global energy crisis and pave the way for a future of sustainable, boundless energy. Tapping into this energy could allow us to overcome many of the environmental and technological challenges we face today. Beyond energy, the study of the vacuum provides insights into some of the most enigmatic phenomena in the universe, such as dark matter and dark energy. These mysterious elements make up the majority of the universe's mass and energy, yet we still know very little about them. Understanding how the vacuum interacts with these elusive components could hold the key to unlocking their true nature, offering answers to some of the biggest questions in cosmology and physics. Additionally, the potential applications of vacuum-related technologies extend far beyond energy and space exploration. The principles of quantum mechanics, which are intricately tied to the properties of the vacuum, have already led to advancements in quantum computing, nanotechnology, and material science. These breakthroughs are not just theoretical, they are shaping the technologies of tomorrow. Quantum computers, for example, have the potential to revolutionize industries by solving complex problems much faster than classical computers. New materials, inspired by vacuum phenomena, could lead to the development of super-efficient conductors or materials with previously unimaginable mechanical properties, transforming everything from manufacturing to medicine. While these applications are still in their infancy, the potential for growth in these fields is immense. As our understanding of the vacuum and its properties deepens, we may find ourselves on the brink of a new technological renaissance. The ability to manipulate quantum fields within the vacuum could unlock a vast array of possibilities, enabling us to develop technologies that were once considered science fiction, such as faster-than-light travel, advanced medical treatments, and even new forms of communication. However, as we move closer to realizing these possibilities, we must also consider the ethical and philosophical implications of such advancements. The ability to manipulate the very fabric of spacetime, to tap into the vacuum's energy, or to develop quantum technologies, brings with it profound responsibilities. How we use this newfound knowledge will shape the future of humanity. It is crucial that we approach these discoveries with caution and foresight, ensuring that they are applied in ways that benefit all of society and do not lead to unintended consequences. The exploration of the cosmic vacuum also forces us to question our fundamental understanding of reality itself. If the vacuum is not truly empty, but teeming with energy and potential, what does this tell us about the nature of existence? Is reality itself merely the manifestation of quantum fluctuations in the vacuum? These questions challenge our deepest philosophical assumptions and invite us to rethink our place in the universe. They also blur the lines between science and philosophy, suggesting that understanding the vacuum may not only provide answers to scientific problems but may also require us to confront profound metaphysical questions about the nature of time, space, and consciousness. In this sense, the study of the vacuum is not just a scientific pursuit, it is a philosophical journey that forces us to rethink the very foundations of reality. As we continue to probe the mysteries of the vacuum, we will not only uncover the secrets of the universe but also redefine our understanding of existence itself. The more we learn, the more we realize that the vacuum is not a mere void but a dynamic, living medium that shapes the entire cosmos. Ultimately, the cosmic vacuum represents the frontier of human knowledge, a vast, unexplored realm filled with infinite potential. It holds the key to understanding the nature of everything, from the smallest particles to the largest cosmic structures. Our ability to harness the properties of the vacuum could transform our world in ways we can scarcely imagine. The quest to unlock its secrets is not just a scientific endeavor, but a journey that will shape the future of humanity and change the course of history. The discoveries made in this field will not only redefine technology and science but will also reshape our deepest philosophical beliefs, challenging us to reconsider the very nature of reality itself. As we stand on the threshold of these discoveries, we can only imagine the incredible possibilities that lie ahead. The cosmic vacuum is not just empty space, it's the canvas on which the entire universe is painted. It is the medium through which all forces and particles interact. Understanding this mysterious void could hold the key to solving some of the most profound questions about the universe, from its origin to its ultimate fate. It is, in many ways, the ultimate frontier, and our exploration of it is only just beginning. This journey into the unknown is not just about solving scientific puzzles, it is about expanding our worldview, challenging our assumptions, and discovering new ways to shape the future. The cosmic vacuum offers us the opportunity to reimagine everything we know about the universe and to build a new, deeper understanding of the very fabric of reality. The exploration of the vacuum is the key to unlocking the mysteries of existence, and its potential is boundless. The journey ahead promises to be one of the most exciting and transformative endeavors in the history of human knowledge. 55 Cancri, located approximately 41 light-years from Earth in the constellation Cancer, is among the most intriguing exoplanets known to science. Orbiting its host star, 55 Cancri A, this distant celestial body challenges astronomers with its extreme and perplexing characteristics. With an orbit completed in just under 18 hours, this planet exists astonishingly close to its star. This proximity causes intense gravitational forces, locking the planet into synchronous rotation. Consequently, one hemisphere endures continuous exposure to blistering heat and radiation, while the other side remains permanently shrouded in darkness and relative cold. Surface temperatures on the illuminated hemisphere soar beyond 2,500 degrees Celsius, creating a vast ocean of molten rock. Constant volcanic eruptions, driven by tidal forces and internal heat, continually reshape the landscape, turning it into an ever-changing inferno. Beneath this molten crust, scientists theorize a thick layer of carbon compressed into solid diamond, a fascinating scenario earning this planet its famous nickname, the Diamond Planet. Yet despite the allure of diamond-rich layers, conditions here are violently inhospitable. The atmosphere, if present, would likely consist of dense, toxic gases, including vaporized metals and silicates, completely hostile to life as we understand it. These brutal conditions have captivated researchers eager to understand planetary processes under extreme environments. What makes this celestial body even more fascinating is how it defies existing theories of planet formation. With a mass roughly 8 times that of Earth, astronomers puzzle over how such a massive rocky planet formed and migrated so close to its star. Studying this phenomenon may fundamentally alter current models of planetary evolution and orbital dynamics. Advanced telescopes such as NASA's James Webb Space Telescope aim to uncover more details about the exoplanet's atmospheric composition, volcanic activity, and potential chemical processes. New insights could emerge from observations, possibly revealing unknown geological phenomena or unprecedented chemical reactions taking place under these extreme conditions. Astronomers speculate about intriguing possibilities such as immense metallic storms or exotic auroras caused by strong magnetic fields interacting with stellar radiation. Others consider the existence of seismic activities or tectonic shifts so powerful that the planetary surface could dramatically change within days. If confirmed, these phenomena would represent entirely new planetary processes unknown within our solar system. Additionally, researchers ponder whether the gravitational interactions with nearby planets could influence internal planetary dynamics, potentially creating rhythmic volcanic cycles or geochemical pulses. Understanding such intricate gravitational resonances could significantly advance our knowledge of planetary systems. Ultimately, this extraordinary exoplanet serves as a natural laboratory, allowing scientists to explore the extremes of planetary physics and chemistry. Each new discovery reveals yet another unexpected mystery, reminding humanity of the infinite complexity and wonder inherent within the cosmos. As scientific exploration of this exotic planet advances, astronomers consider increasingly daring theories. Could the intense gravitational interactions with its star create powerful internal magnetic fields, generating spectacular electromagnetic phenomena such as metal-rich auroras? If so, telescopes might someday detect these dazzling displays, fundamentally reshaping our understanding of planetary magnetism. Moreover, some researchers theorize about the potential for rapid orbital decay, where tidal interactions gradually pull the planet even closer to its star. Observing such a dramatic event would provide unprecedented insight into planetary destruction and offer direct evidence of the dynamic nature of planetary orbits. Another exciting possibility involves transient geological phenomena driven by the extreme internal pressure and heat. Scientists speculate that beneath the molten surface, conditions may periodically produce exotic mineral formations or even temporary states of plasma-like materials. Capturing observational signatures of these phenomena could significantly expand our geological knowledge. Intriguingly, astronomers also imagine how this carbon-rich planet's extreme conditions might foster unique chemical reactions. Could the intense stellar radiation and high temperatures drive previously unknown photochemical or nuclear processes, generating new molecules or isotopes? Detecting such compounds would challenge existing chemical theories and inspire entirely new fields of astrochemical research. Future technologies, including specialized instruments and powerful observatories, might soon allow scientists to detect subtle variations in the planet's emitted radiation, providing clues about hidden internal processes. Detailed studies of atmospheric composition, surface volcanism, and magnetic interactions with the star could reveal unexpected cycles or rhythms, offering insights into planetary stability under extreme conditions. Additionally, researchers consider whether the extreme geological activity might occasionally propel mineral-rich debris or diamond particles into orbit, forming transient rings or clouds around the star. Capturing visual evidence of such events would dramatically illustrate how planets influence their stellar environments. Each new theory and discovery about this distant world not only expands our scientific horizons but also deepens humanity's philosophical reflections about the nature of the universe itself. By challenging existing models and inviting speculation about previously unimaginable processes, this extraordinary exoplanet continues to ignite scientific curiosity, driving humanity to push the boundaries of exploration ever further into the cosmic unknown. As astronomers continue probing the mysteries of this extraordinary exoplanet, speculation emerges regarding hidden, deeper phenomena beneath its volcanic surface. Could enormous subsurface currents or tides of molten rock circulate within the planet's interior, driven by gravitational friction and internal heating? Detecting these hidden magma currents could revolutionize our understanding of planetary geology under extreme gravitational stress. Furthermore, scientists theorize the existence of unusual seismic activity, perhaps massive tectonic movements or planet-wide tremors caused by tidal forces. If observable from Earth, these seismic events could offer invaluable insights into the structural integrity and geological processes of rocky planets under intense gravitational conditions. Another captivating possibility is the formation of entirely new, transient minerals created by extreme pressures and temperatures beneath the planet's crust. These minerals might appear and vanish rapidly, cycling in response to volcanic eruptions and internal pressures. Observations capturing these fleeting geological events could significantly enhance our knowledge of mineral formation processes under extraordinary planetary environments. Researchers also consider the potential for dynamic atmospheric phenomena. Could vaporized metals form turbulent storms or metallic rain, periodically reshaping the planetary surface? Detecting atmospheric events composed of vaporized silicates, iron, or other exotic materials would profoundly expand our understanding of planetary weather systems. Moreover, the planet's proximity to its star raises questions about complex magnetic interactions. Powerful stellar winds interacting with the planet's magnetic field might generate astonishing auroral displays or electromagnetic storms detectable by advanced telescopes. Understanding these interactions could provide crucial data for refining theories about planetary magnetic fields and stellar influences. This fascinating world also inspires questions about how planets evolve under extreme orbital migrations. If the planet once orbited farther from its star, how did it migrate inward, and what violent interactions forced this change? Analyzing such orbital history could yield valuable insights into planetary formation and the stability of planetary systems. In the future, groundbreaking observational techniques, perhaps even remote seismic measurements or highly detailed spectroscopic analysis, could allow astronomers to study surface movements or atmospheric changes directly. Such advances would offer an unprecedented glimpse into the real-time dynamics of distant worlds, transforming exoplanetary research. Ultimately, the continued exploration of this intriguing exoplanet emphasizes humanity's insatiable curiosity about cosmic extremes. Each new discovery pushes us to reimagine what planets can be, driving scientific innovation and reinforcing the awe-inspiring complexity and creativity of the universe. Further exploration into this captivating exoplanet invites us to consider scenarios previously unexplored by planetary science. For example, scientists have begun theorizing about the intriguing possibility that gravitational resonances between the planet and other bodies within the 55 Cancri system could trigger episodic surface upheavals. These hypothetical gravitational tides might periodically fracture the crystalline diamond layers beneath the molten crust, releasing vast quantities of carbon-rich materials and fueling massive volcanic eruptions visible even from Earth-based telescopes. Moreover, researchers speculate about whether this exotic planet might exhibit magnetic reversals far more rapid and chaotic than those recorded on Earth. Such extreme fluctuations could result from the planet's rapid rotation, intense tidal stresses, and highly conductive molten interior. Observing these shifts in magnetic orientation remotely would offer unprecedented evidence of how planetary magnetic fields behave under extreme conditions, potentially transforming astrophysical theories. Astronomers also envision scenarios where the planet's immense heat and gravitational forces might occasionally generate enormous atmospheric eruptions, storms composed of vaporized metals or rapidly condensing diamond dust. These events could briefly alter the planet's reflective properties or spectral signature, providing rare glimpses into transient planetary processes. Capturing these phenomena could yield extraordinary insights into the exotic chemistry and atmospheric dynamics occurring at the fringes of planetary science. The planet's volatile surface environment might also result in cyclical chemical processes, where exposure to intense stellar radiation continuously drives transformations in surface chemistry. Complex cycles of melting, crystallization, and sublimation could repeatedly alter the surface composition, forming compounds and crystals previously unseen in nature. Studying these chemical cycles might significantly expand our understanding of mineral stability under cosmic extremes. Another captivating question is whether gravitational interactions with its host star could result in subtle shifts in stellar behavior itself. Could this planet's relentless gravitational tug influence stellar activity, magnetic cycles, or flare production? If such a planetary-stellar connection were confirmed, it would fundamentally reshape how scientists perceive the relationships between stars and their orbiting worlds. The exoplanet's extreme nature also inspires ideas about future exploration technologies. Advanced observational platforms, employing high-resolution spectroscopy and gravitational wave detectors, may soon capture precise data about surface movements, internal seismic activity, or even atmospheric chemistry. Such data would provide groundbreaking insights into planetary behaviors in extreme environments. Finally, this compelling exoplanet symbolizes humanity's drive to push beyond conventional limits, constantly challenging what we believe possible. Each new revelation encourages astronomers and scientists alike to venture further into the unknown, forever expanding our view of a universe filled with endless diversity, beauty, and mystery. As our exploration deepens into the mysteries surrounding this exceptional exoplanet, new speculative ideas continue to captivate researchers. Some astronomers propose the existence of colossal underground caverns or voids deep beneath its molten surface, spaces carved by enormous pressure fluctuations, gravitational shifts, or tidal forces. Within these vast subterranean chambers, unique mineral deposits or exotic crystalline formations could exist, isolated from the turmoil raging on the surface. Such hidden realms would profoundly expand our understanding of geological processes under unprecedented planetary conditions. Equally intriguing is the potential discovery of periodic shifts in the planet's magnetic field intensity, generated by interactions between its dynamic interior and fierce gravitational forces. Could these magnetic fluctuations trigger remarkable electromagnetic events, observable as pulses of radiation or magnetic storms visible from Earth-based instruments? Detecting such phenomena would offer incredible opportunities for astrophysicists to study magnetic dynamics under extremes never previously encountered. Scientists are also fascinated by the possibility of this planet periodically ejecting significant portions of its atmosphere or surface material into space due to explosive volcanic activity or tidal disruptions. Such dramatic events could create temporary clouds of vaporized rock and diamond particles orbiting the star, altering the system's brightness or spectral signals. Capturing observational evidence of these cosmic spectacles would provide extraordinary proof of how planetary systems evolve and influence their stellar surroundings. Additionally, speculation grows about whether extreme chemical reactions driven by intense stellar radiation and gravitational forces could produce exotic, transient compounds with novel chemical bonds or even new forms of carbon-based matter. Detection of such chemical innovations would revolutionize astrochemistry and perhaps open entirely new possibilities in material science. Even gravitational theories might evolve from studying the dynamics of this peculiar world. Could the planet's orbit exhibit subtle yet measurable gravitational anomalies, minute irregularities pointing to previously unknown physical interactions between massive planets and their stars? Analyzing these orbital variations could refine gravitational models and deepen our fundamental understanding of gravity's role in shaping planetary systems. Furthermore, this distant planet's extreme nature raises broader scientific curiosity regarding planetary classification itself. Could it represent a previously unrecognized planetary type, one defined by extreme geological processes, rapid orbital dynamics, and unconventional chemistry? If so, identifying and understanding this new class of celestial bodies would significantly reshape planetary science, broadening our cosmic perspective. Each revelation about this extraordinary exoplanet highlights how exploration of extreme worlds continuously expands scientific imagination. In studying such enigmatic places, humanity comes face to face with questions that challenge our assumptions and stimulate revolutionary discoveries, fueling both scientific progress and a deeper appreciation of the universe's boundless diversity. Delving further into the mystery of this captivating exoplanet, astronomers imagine even more profound scenarios unfolding beneath its fiery facade. For instance, could the continuous, intense stellar radiation trigger electromagnetic phenomena at the planet's surface, potentially generating localized magnetic anomalies or plasma-based phenomena? Detecting these exotic surface activities could open up entirely new areas of astrophysical research and lead scientists toward unexplored physics governing stellar planetary interactions. Additionally, the planet's extreme gravitational forces might produce remarkable geological activity unlike anything encountered within our solar system. Researchers speculate about the existence of rapidly evolving volcanic mountain ranges or constantly shifting continental plates composed of solidified carbon structures. Such active geology, changing visibly within short periods, would provide an unprecedented opportunity to study planetary tectonics operating under conditions dramatically different from Earth. There is also speculation about hypothetical phenomena known as diamond rain occurring within the planet's atmosphere, where vaporized carbon compounds might condense into tiny diamond particles, gradually falling back onto the molten surface. Capturing observational signatures of these spectacular events could dramatically enhance our understanding of exotic weather systems and offer tangible evidence of how chemistry operates in extraordinarily harsh environments. The planet's gravitational influence on its host star might even extend further, possibly inducing subtle stellar pulsations or magnetic fluctuations. Observations of such star-planet interactions would yield remarkable insights into the mutual gravitational effects between massive terrestrial worlds and their parent stars, reshaping how we interpret planetary evolution in extreme environments. Researchers also theorize about the existence of transient atmospheric windows, brief periods when volcanic activity subsides enough to allow clearer observations into the deeper layers of its atmosphere or surface. Exploiting these moments with precise telescopic observations could provide invaluable opportunities to gather data about atmospheric compositions or volcanic activity previously obscured by constant geological turmoil. Moreover, some scientists envision that the planet's extreme gravitational conditions might occasionally produce gravitational waves or seismic tremors detectable by advanced observational instruments from Earth. Such groundbreaking detections would offer astronomers the unprecedented ability to study planetary geology directly through gravitational wave astronomy, pioneering a remarkable new frontier of cosmic observation. Exploring worlds like this fiery super-Earth continually pushes human knowledge forward, inspiring innovation in astronomy, astrophysics, geology, and even philosophical reflection on our cosmic place. Each discovery encourages humanity to look further, to question deeper, and to appreciate more fully the boundless mysteries still awaiting exploration among the stars. Scientists exploring the extraordinary nature of this distant super-Earth now also ponder another fascinating possibility: the planet's capacity for exotic seismic phenomena. Could powerful tidal forces trigger global planet quakes, causing seismic vibrations capable of reshaping the planet's molten landscape overnight? If such seismic events occur regularly, they might influence volcanic eruption patterns, atmospheric dynamics, or even surface chemistry in ways never before observed. Equally intriguing is the potential existence of exotic interactions deep within its molten interior, phenomena such as spontaneous formation of novel carbon-based alloys, superconductive crystals, or even complex compounds born from the interplay between extreme pressure and heat. Discovering these hidden geochemical processes would significantly advance our understanding of how extreme planetary environments can produce unexpected chemical states of matter. Scientists are also considering how the planet's extreme gravitational relationship with its host star might influence stellar flares or magnetic storms, potentially causing episodic bursts of stellar radiation. Detecting these interactions would demonstrate that planets, even rocky super-Earths, might significantly affect the behavior of their host stars, an exciting possibility previously reserved mostly for giant planets like Jupiter. Furthermore, astronomers speculate that subtle gravitational waves, ripples in spacetime caused by intense planetary star interactions, could emanate periodically from this system. Advanced gravitational wave observatories of the future might someday detect faint signals from these distant tidal interactions, providing groundbreaking evidence of planet-star gravitational dynamics on a cosmic scale. Additionally, the extreme temperature gradients between the planet's eternally hot daylight side and permanently shadowed hemisphere could create powerful global convection currents in its atmosphere, driving massive, hurricane-like storms of molten vaporized minerals. Observing these spectacular planetary storms would offer unprecedented insight into atmospheric dynamics under severe thermal stress. Even speculative discussions of hidden planetary oceans, not of water but of liquid carbon or molten metals, beneath its blistering crust continue to intrigue planetary scientists. Such bizarre oceans might host unexpected geochemical reactions, possibly generating transient mineral formations or even unusual chemical cycles that continuously alter the planet's internal structure and surface chemistry. Ultimately, each fresh observation about this captivating exoplanet further reveals the immense complexity and creativity of nature, continually redefining the boundaries of planetary science and exploration. As telescopes and technology advance, astronomers remain confident that this distant and mysterious world will continue to yield remarkable discoveries, deepening our curiosity about the limitless diversity of planetary conditions throughout the universe. As astronomers continue unraveling the fascinating mysteries surrounding this enigmatic celestial body, the possibility emerges that beneath its scorching surface might lie hidden gravitational anomalies capable of influencing planetary structure at microscopic scales. These subtle anomalies could trigger localized pulses of extreme pressure, potentially creating transient pockets of exotic crystalline structures, briefly formed, then shattered by violent geological upheavals. If such transient geological formations exist, their discovery could dramatically enhance our understanding of planetary interiors under unprecedented stress conditions. Researchers also speculate whether sudden bursts of intense volcanic activity might periodically reshape the planet's atmosphere, ejecting enormous clouds of vaporized metals and minerals into orbit. Such explosive eruptions could temporarily envelop the planet in reflective metallic clouds visible from Earth, creating spectacular changes in brightness and spectral signatures. Observing these dramatic planetary scale events would provide invaluable insight into extreme volcanism and atmospheric evolution on worlds experiencing relentless stellar radiation. Even more provocative are theories suggesting that the planet's extreme gravitational environment might drive exotic quantum phenomena deep beneath the molten surface. Could the immense pressures and heat generate fleeting states of matter, such as metallic carbon alloys or superconducting crystals, that briefly emerge before disintegrating into molten chaos? If detected, these short-lived phenomena could prompt scientists to reconsider fundamental theories about the stability and diversity of matter in the cosmos. Astronomers are also intrigued by the possibility that gravitational interactions within the planet's orbit might create complex resonances or harmonic patterns involving neighboring planetary bodies. Such subtle gravitational interplay could influence internal geological processes, perhaps triggering rhythmic eruptions, seismic activity, or atmospheric fluctuations on predictable intervals. Understanding these subtle resonances might open entirely new avenues in planetary dynamics research, offering deeper insights into how planetary systems evolve and sustain stability. Another fascinating question arises about the planet's magnetic environment. Could intense internal friction and tidal stresses generate electromagnetic pulses or bursts detectable from Earth? Observing such phenomena might not only revolutionize our understanding of planetary magnetism but also help scientists identify new ways to search for and characterize extreme planets in other star systems across our galaxy. In addition, some scientists propose future technologies might someday enable direct imaging or remote analysis of transient geological events, such as sudden resurfacing of solid diamond layers, temporary magma lakes, or storms of metallic vapors, transforming our theoretical understanding into observable reality. Developing these advanced observational capabilities would profoundly advance astronomy, expanding humanity's ability to witness planetary phenomena in unprecedented detail. Ultimately, this distant, enigmatic planet symbolizes both the infinite complexity and boundless potential of the universe. Each unanswered question and surprising discovery fuels human curiosity, continually inspiring scientists to explore further, question deeper, and imagine wider, pushing the limits of our cosmic understanding and revealing that the universe is vastly richer and more astonishingly diverse than we ever dreamed possible. Continuing exploration of this extraordinary exoplanet raises increasingly provocative questions about how planets behave in extreme stellar proximity. Astronomers contemplate whether gravitational interactions might induce unusual planetary pulsations, rhythmic expansions or contractions of the planet's interior, driven by tidal forces from its star. Such pulsations could periodically alter the planet's density distribution, potentially affecting volcanic activity, seismic events, or even the structure of its hypothesized diamond core. Moreover, the extreme conditions of this planet inspire ideas about previously unseen atmospheric chemistry. Could ongoing volcanic eruptions and stellar radiation combine to form dynamic cycles of chemical reactions, creating transient atmospheres composed of exotic gases or particles never before documented? Detecting such phenomena could transform our understanding of atmospheric chemistry under severe stellar bombardment. Intriguing also is the possibility that intense surface conditions might produce exotic forms of lightning, generated by friction and collisions within dense metallic clouds. Imagine massive electrical storms spanning continents of molten rock, illuminating the perpetual twilight regions between blazing daylight and absolute darkness. Capturing evidence of these spectacular electric phenomena would not only amaze scientists but also provide crucial insights into electrical processes on extreme worlds. Another compelling scenario involves planetary-scale convection currents, driven by extreme temperature differences between the illuminated and dark hemispheres. These currents might continuously transport heat, minerals, and carbon-rich matter around the planet, creating cycles of geological renewal and destruction. Detecting evidence of such planetary-scale circulation could revolutionize geophysical models and enhance our understanding of internal planetary dynamics. Scientists also consider whether extreme orbital conditions could lead to unusual patterns in surface gravity, possibly producing areas of shifting gravitational intensity across the planet's landscape. These gravitational anomalies might periodically trigger massive collapses or eruptions, creating a uniquely chaotic and unpredictable surface environment. Studying such gravitationally driven phenomena would deepen our comprehension of planetary surface behavior under extreme conditions. Additionally, some researchers ponder the possibility of observing reflections of stellar radiation from transient atmospheric structures or layers of crystallized carbon temporarily exposed by volcanic activity. Detecting spectral variations indicating brief windows into otherwise hidden planetary layers would provide astronomers with valuable information about its geological composition and evolution. Ultimately, each new question and discovery surrounding this fascinating planet underscores humanity's endless quest for cosmic understanding. By exploring worlds of unimaginable extremes, astronomers continually expand the boundaries of our knowledge, inspiring generations to dream of discoveries yet to be made and phenomena yet to be imagined. Astronomers continue to theorize about hidden mysteries deeper beneath this planet's fiery exterior, suggesting possibilities even more exotic and captivating. Could powerful gravitational resonances within its planetary system occasionally trigger immense internal pressure waves, propagating through the planet's molten layers, causing dramatic surface upheavals? Such phenomena, if detected, might unveil a cosmic rhythm underlying planetary systems, enhancing our understanding of celestial dynamics. Furthermore, the extreme pressures at the planet's core might foster states of matter entirely unknown to modern physics, perhaps transient phases of matter where diamond, graphite, or metallic carbon exist simultaneously in fleeting equilibrium. Discovering these transient materials could offer breakthroughs in materials science, influencing our understanding of carbon's versatility and potential under extreme conditions. Astronomers are also fascinated by the potential for observing transient events such as immense volcanic explosions powerful enough to alter the planet's reflectivity or even temporarily obscure its visibility. Witnessing these explosive events from Earth-based telescopes would provide rare and invaluable data, showcasing planetary processes on a scale previously impossible to study. Additionally, the planet's surface might periodically experience massive fractures, through which molten interior materials erupt with unprecedented force. Such volcanic episodes could temporarily expose interplanetary layers, offering scientists rare windows into its geological and chemical evolution. Documenting these brief episodes would significantly advance theories regarding planetary interiors and volcanic activity under extreme gravitational stress. Researchers are also intrigued by the possibility of electromagnetic interactions between the planet's molten surface and the stellar wind emitted by its host star. Such interactions might produce spectacular electromagnetic phenomena, including intense radiation pulses or magnetic storms. Detecting and analyzing these interactions could vastly expand our knowledge of planetary magnetospheres under conditions far beyond those observed in our solar system. Finally, each theory, observation, and unanswered question surrounding this intriguing world highlights how exploration of extreme planetary environments reshapes human knowledge. This distant exoplanet continuously challenges our scientific imagination, compelling astronomers to envision extraordinary possibilities, pushing humanity toward ever greater discoveries among the infinite wonders of the cosmos. Astronomers also wonder whether intense tidal interactions might periodically trigger dramatic shifts within the planet's magnetic field, perhaps even flipping its magnetic poles at intervals far shorter than anything known elsewhere. If detectable, such rapid magnetic reversals would astonish planetary scientists, challenging fundamental assumptions about how magnetic fields evolve and persist under extreme gravitational stress. Researchers speculate further about whether powerful gravitational forces might induce massive planetary quakes, capable of fracturing even thick diamond layers deep beneath the molten surface. Such seismic activity could produce distinct patterns of tremors detectable remotely by advanced telescopes, providing groundbreaking insights into seismic phenomena far beyond Earth's experience. Intriguingly, atmospheric studies raise questions about the possibility of transient chemical reactions triggered by sudden spikes in stellar radiation. These brief, high-energy events might generate exotic carbon compounds, vaporized metals, or unique atmospheric aerosols, creating momentary spectral signatures detectable from Earth. Observing these fleeting chemical changes could significantly advance astrochemistry, pushing scientists to explore entirely new reaction pathways. There is also fascination around the concept that violent geological processes on this planet might periodically release immense jets of vaporized minerals, carbon-rich particles, or even diamond fragments into space, briefly creating dazzling cosmic phenomena around its star. Capturing direct evidence of such stellar ring interactions would profoundly influence our understanding of planetary evolution and stellar environments. Additionally, astronomers are intrigued by the possibility of gravitational resonances involving neighboring planets, potentially causing subtle orbital instabilities or complex planetary alignments. Could the planet's internal dynamics respond dynamically to such gravitational interactions, resulting in cyclic volcanic activities or predictable seismic episodes? Understanding these gravitational resonances would enrich theories of planetary interactions and orbital stability. Finally, each new insight from studying this enigmatic world underscores humanity's endless capacity for discovery and imagination. By probing the extremes, scientists continually refine theories of planetary science, challenging accepted knowledge and inspiring new ideas about the possibilities and limits of cosmic phenomena. This extraordinary exoplanet thus remains a constant reminder of the boundless mysteries awaiting us, urging humanity onward into deeper exploration of the universe's astonishing diversity. Delving even further into the mysteries of this captivating planet, astronomers propose scenarios involving gravitational influences so extreme they might produce unforeseen planetary behaviors. Could intense gravitational interactions trigger rhythmic expansions and contractions of the planet's molten layers, creating tidal pulses detectable across interstellar distances? Observing such phenomena would reveal extraordinary insights into how gravitational energy shapes planetary interiors. Furthermore, the extreme temperatures and pressures beneath the surface could yield short-lived but astonishing geological events, such as sudden crystallization of carbon-rich magma into transient islands of diamond or graphite, which would rapidly melt again under volcanic heat. Capturing observational signatures of these transient crystalline structures could significantly enhance our understanding of matter's behavior under extreme planetary conditions. Scientists also speculate about potential atmospheric cycles involving exotic chemical weather patterns. Could volatile metallic vapors condense periodically into intense metallic storms, raining droplets of iron, silicate, or even diamond dust across vast molten seas? Detecting such exotic meteorological phenomena would dramatically broaden humanity's perception of possible planetary climates. Intriguingly, astronomers theorize the existence of powerful, short-lived electrical storms, created by frictional interactions within clouds of vaporized rock and metal. These spectacular electrical phenomena, if detectable from Earth, would not only fascinate observers but also advance our understanding of electromagnetic processes in planetary atmospheres. Another compelling concept involves gravitational wave astronomy. Could intense tidal interactions between the planet and its host star emit faint gravitational waves detectable by future astronomical observatories? Observing these subtle gravitational signals would revolutionize planetary astronomy, opening entirely new observational methods to study distant worlds. In addition, advanced telescopes might someday capture direct evidence of planetary-scale eruptions capable of temporarily reshaping the planet's visible surface or altering its reflective properties dramatically. Such discoveries would offer extraordinary real-time insights into planetary geology operating under unimaginable stresses. Ultimately, this intriguing planet embodies the endless possibilities and wonders inherent in cosmic exploration. Each new theory and observational breakthrough deepens humanity's awe at the infinite complexity and creativity of the universe, continually inspiring astronomers to explore beyond known limits and discover ever more astonishing phenomena among the stars. Continuing exploration into the captivating mysteries surrounding this extraordinary celestial body leads scientists to speculate on even more exotic planetary phenomena. Could extreme tidal stresses create transient planetary geysers, erupting violently from beneath the surface, sending jets of molten material and vaporized diamond particles into the surrounding space? Detecting such explosive events would offer incredible insights into volcanic processes on worlds experiencing intense gravitational interactions. Additionally, researchers wonder whether intense radiation from its star might periodically cause sudden, global atmospheric expansions or contractions, triggering spectacular fluctuations detectable through precise spectroscopic observations. Witnessing such rapid atmospheric pulsations could fundamentally reshape our understanding of planetary atmospheres subjected to severe stellar radiation. Astronomers are also intrigued by the possibility that beneath the turbulent surface, immense internal currents of molten rock might generate spontaneous electromagnetic phenomena, potentially producing localized regions of extreme magnetic anomalies or plasma activity. Capturing evidence of these electromagnetic disturbances would revolutionize theories about planetary magnetospheres under extreme conditions. Furthermore, researchers theorize that gravitational influences from nearby planets might occasionally create subtle yet measurable variations in this planet's orbit. Studying these orbital perturbations could reveal previously unknown gravitational resonances within the planetary system, helping astronomers understand how planets evolve dynamically over cosmic timescales. Moreover, some planetary scientists suggest the existence of transient crystalline structures forming within the atmosphere itself, perhaps temporary clouds or haze layers composed of vaporized minerals or diamond-like carbon particles. Detecting and analyzing these ephemeral formations would greatly advance our knowledge of atmospheric chemistry under extraordinary planetary environments. Finally, as humanity's observational capabilities continue to improve, future discoveries about this enigmatic exoplanet promise to reveal phenomena currently beyond imagination. Each new insight gained from studying such an extreme celestial body underscores our profound curiosity, continually pushing astronomers to redefine scientific boundaries and inspiring humanity to explore ever deeper into the universe's boundless wonders. As astronomers venture deeper into understanding this compelling celestial object, speculative possibilities become increasingly daring. Could gravitational interactions induce previously unseen planetary phenomena, such as temporary formations of immense magnetic vortices or localized magnetic storms across its molten surface? Capturing evidence of these extraordinary magnetic disturbances would profoundly alter existing theories of planetary magnetism and dynamics. Researchers also contemplate whether intense tidal stresses from the planet's close orbit might periodically compress or expand its internal layers, generating dramatic fluctuations in volcanic and seismic activity. Detecting such rhythmic geological events could open entirely new fields of study in planetary geology and seismic processes under extreme gravitational influence. Intriguingly, the planet's harsh environment might periodically trigger massive atmospheric disturbances, perhaps immense storms capable of temporarily disrupting or reshaping the entire planetary atmosphere, resulting in dramatic changes observable through spectroscopy or direct imaging. These atmospheric upheavals would provide invaluable insights into planetary climate dynamics under severe stellar radiation and gravitational stress. Scientists further theorize about exotic chemical phenomena that might occur deep beneath its fiery crust. Could extreme internal pressures and temperatures produce short-lived, exotic carbon-based materials or even transient superconductors beneath its molten seas? Observing or indirectly detecting these materials could lead to revolutionary breakthroughs in materials science, influencing technologies far beyond planetary science. Moreover, astronomers wonder whether gravitational interactions with the star might occasionally trigger planetary-scale electromagnetic pulses, creating brief bursts of electromagnetic radiation detectable across interstellar distances. Confirming such extraordinary electromagnetic events would dramatically reshape our understanding of planetary star magnetic interactions and expand methods of detecting exoplanetary activity. In addition, advanced telescopes and future observational platforms might soon allow astronomers to observe subtle gravitational waves emanating from this planet-star system. Detecting gravitational waves caused by extreme tidal interactions would transform our knowledge of planetary physics, opening an entirely new observational frontier. Ultimately, each intriguing possibility associated with this remarkable planet underscores humanity's ceaseless desire for cosmic discovery. By challenging scientific boundaries and inspiring continual exploration, this distant, enigmatic exoplanet represents an endless source of wonder, pushing astronomers to venture further into the mysteries of the universe. Continuing their investigation into this extraordinary celestial body, scientists envision even more remarkable possibilities. Could intense tidal stresses occasionally trigger planetary-scale tsunamis of molten rock, surging across the surface with unimaginable speed and force? Capturing observational evidence of such volcanic tsunamis would profoundly alter our understanding of geological dynamics under extreme gravitational interactions. Further speculation involves the planet's potential to undergo rapid chemical transformations driven by stellar radiation and extreme heat. Could surface materials periodically vaporize into temporary atmospheres rich in exotic carbon compounds or metallic gases, only to condense back into solid form moments later? Documenting these ephemeral chemical cycles would greatly advance our comprehension of planetary chemistry under conditions far exceeding Earth's extremes. Astronomers also hypothesize about the existence of hidden internal oscillations deep within the planet's core, driven by gravitational friction and pressure fluctuations. These oscillations might periodically release immense bursts of energy, generating detectable electromagnetic or gravitational signals. Confirming such internal planetary pulses would significantly broaden our understanding of planetary interiors and their response to gravitational forces. Additionally, researchers speculate whether transient rings or orbital debris fields composed of vaporized minerals, metallic particles, or even diamond fragments might form following massive volcanic eruptions. Detecting such short-lived orbital structures would dramatically enhance our understanding of how planets interact with and influence their immediate space environments. Scientists further ponder the potential existence of localized electromagnetic storms driven by frictional interactions between vaporized metallic clouds. Could these storms generate extraordinary lightning phenomena visible through advanced spectroscopic analysis? Observing such electrical activity would expand our knowledge of atmospheric electricity in extreme planetary conditions. Ultimately, every intriguing question and bold hypothesis surrounding this enigmatic planet fuels humanity's endless curiosity about the cosmos. Each discovery pushes us further into realms previously unimagined, constantly challenging scientific paradigms and reminding us that the universe's creativity and complexity remain infinitely beyond our current understanding. Exploring this exceptional planetary environment even further, astronomers propose increasingly imaginative scenarios. They wonder if intense tidal interactions might produce periodic gravitational pulses strong enough to briefly warp or distort the planet's shape, causing remarkable deformation events visible through advanced observational technologies. Capturing these transient planetary distortions would offer unprecedented insights into planetary elasticity and internal structure under severe gravitational stress. Additionally, the planet's extreme proximity to its star could result in dramatic surface evaporation events, where sudden spikes in stellar radiation vaporize vast areas of molten rock. These evaporative episodes could produce spectacular transient atmospheres detectable through precise spectroscopic observations. Confirming such volatile phenomena would significantly enhance our understanding of planetary surface-atmosphere interactions in extreme stellar environments. Researchers also envision the intriguing possibility of giant, temporary fissures opening across the planetary surface due to internal pressures and gravitational stresses, briefly exposing deeper layers of crystalline diamond or exotic minerals. Observing these short-lived geological features would provide remarkable opportunities to study planetary geology under previously unimaginable conditions. Moreover, scientists speculate about potential gravitational resonances with neighboring planets that might periodically amplify internal volcanic and seismic activities, creating predictable geological cycles. Unraveling these gravitational interactions would greatly expand knowledge of planetary system dynamics and their long-term stability. Further theoretical possibilities include extreme electrical phenomena beneath the molten surface, perhaps driven by friction between different internal layers. Could these internal electrical currents occasionally burst forth, generating electromagnetic pulses or transient magnetic storms detectable from Earth? Discovering evidence of such hidden electromagnetic activities would reshape current planetary magnetic theories. Ultimately, each daring speculation and potential discovery surrounding this remarkable exoplanet emphasizes humanity's ceaseless quest to understand cosmic extremes. By continuously expanding our scientific imagination, astronomers reaffirm that the universe remains full of astonishing mysteries awaiting exploration, forever challenging our perceptions and inspiring future generations to venture deeper into the cosmos. As humanity's exploration of this extraordinary exoplanet continues, each new discovery, observation, and bold hypothesis fuels a deeper understanding of planetary extremes. Every scenario imagined, from gravitational pulses reshaping its surface to transient magnetic storms and molten tsunamis, challenges existing scientific boundaries and propels our knowledge toward unexplored realms. Future astronomical missions, employing technologies not yet invented, promise even more precise insights. Advanced telescopes equipped with hypersensitive spectrographs may soon capture previously unseen details of surface eruptions, atmospheric upheavals, or electromagnetic phenomena. Remote gravitational wave observatories could one day detect subtle vibrations from seismic events deep within the planet's core, opening a revolutionary chapter in planetary science. Moreover, lessons learned from studying this extreme world could guide humanity's search for potentially habitable planets elsewhere, refining our understanding of planetary habitability by highlighting which environmental factors support stability, or trigger catastrophic destruction. The extreme geology, magnetism, and atmospheric chemistry observed here could reshape our expectations of how life-supporting conditions might arise or fail elsewhere. Finally, beyond the scientific discoveries and technological advancements, exploring this distant, mesmerizing planet serves as a powerful reminder of humanity's innate desire to explore the unknown. Each question answered generates new, profound questions, eternally pushing us to expand our perspectives and continue seeking. In studying worlds of astonishing extremes, we reaffirm our curiosity and resilience, ensuring humanity's journey of cosmic discovery will forever remain endless, compelling, and inspiring.
Neptune, the eighth and most distant planet from the Sun in our solar system, represents one of the most enigmatic and fascinating objects of astronomical study. Its discovery, physical characteristics, atmosphere, magnetosphere, moons, and ring system provide a wealth of scientific interest, extending our understanding of planetary formation, dynamics, and the diverse environments within our solar system. Neptune was discovered on September 23, 1846, by Johann Galle, based on predictions by Urbain Le Verrier and John Couch Adams. Unlike other planets that were found through direct observation, Neptune's existence was hypothesized due to irregularities in the orbit of Uranus. These irregularities suggested the gravitational influence of another massive object. Le Verrier calculated the probable position of this object, leading to its subsequent observation. This marked a milestone in celestial mechanics and validated Newtonian physics on an interplanetary scale. Neptune's physical characteristics reveal it as a gas giant, though it is often categorized along with Uranus as an ice giant due to its unique composition. With a diameter of approximately 49,244 kilometers, it is nearly 4 times the size of Earth. Its mass, about 17 times that of Earth, makes it the densest of the gas giants. The planet's composition is dominated by hydrogen and helium, but it also contains significant amounts of water, ammonia, and methane. These compounds exist in various states due to extreme pressures and temperatures, creating layers of exotic ices beneath its atmosphere. The planet's vibrant blue appearance, a hallmark of its visual identity, is largely attributed to methane in its atmosphere, which absorbs red light and reflects blue. However, there are likely additional, as yet unidentified components contributing to its unique coloration. The dynamic atmosphere of Neptune is characterized by extreme weather phenomena. Winds on Neptune are the fastest in the solar system, reaching speeds of up to 2,100 kilometers per hour. These winds drive massive storms, such as the Great Dark Spot observed by the Voyager 2 spacecraft in 1989, a storm comparable in size to Earth. This feature was transient, disappearing within a few years, but other dark spots have since been observed, indicating the continual formation and dissipation of such systems. The planet's internal structure is less well understood, but is believed to consist of a rocky core surrounded by a mantle of water, ammonia, and methane ices. This mantle transitions into the atmosphere, creating a gradual boundary rather than a distinct separation. The extreme pressures and temperatures within Neptune's interior may lead to the formation of exotic materials, such as superionic water and diamond rain. These phenomena are subjects of active research and provide valuable insights into the behavior of matter under extreme conditions. Neptune's magnetosphere is another area of intense study. The planet's magnetic field is tilted by about 47 degrees relative to its rotational axis and is offset from the planet's center. This unusual configuration creates a highly dynamic magnetosphere that interacts with the solar wind in complex ways. The mechanisms behind this magnetic field and its asymmetry are thought to be linked to the conductive materials in the planet's interior, differing significantly from the dynamo processes observed in terrestrial planets like Earth. The study of Neptune's moons, particularly Triton, has revolutionized our understanding of planetary satellites. Triton, the largest of Neptune's 14 known moons, is unique in several ways. It is the only large moon in the solar system with a retrograde orbit, suggesting it was likely a captured Kuiper Belt object. Triton's surface is a mosaic of cryovolcanic plains, frozen lakes, and cantaloupe terrain, shaped by ongoing geological activity. The presence of nitrogen geysers on Triton provides evidence of subsurface reservoirs of liquid nitrogen or other volatile materials. This activity positions Triton as a potential analog for icy bodies in the outer solar system, including Europa and Enceladus. Neptune also has a faint and complex ring system, composed primarily of dark, dusty particles. These rings, named after astronomers who contributed to Neptune's study, include Adams, Leverrier, Lassell, Arago, and Galle. The Adams ring is particularly notable for its arcs, or denser clumps of material that defy the expected uniform distribution. These arcs challenge existing models of ring dynamics and raise questions about the role of shepherd moons or other stabilizing mechanisms. In addition to its intrinsic properties, Neptune serves as a window into broader astrophysical phenomena. Its position and composition offer insights into the processes of planetary migration and the structure of the early solar system. Neptune's orbit is in resonance with several Kuiper belt objects, including Pluto, highlighting the gravitational interplay that shapes the outer regions of our solar system. Exploration of Neptune has been limited but transformative. The Voyager 2 spacecraft provided the first close-up observations of the planet during its flyby in 1989. This mission revealed much of what we know about Neptune's atmosphere, magnetic field, and moons. However, no spacecraft has orbited Neptune, and future missions are critical to addressing the many unanswered questions. Proposed concepts, such as orbiters and atmospheric probes, aim to study the planet's interior, weather systems, and potential for hosting subsurface oceans on its moons. Neptune's significance extends beyond our solar system. Exoplanet research has identified many Neptune-like planets around other stars, often in close orbits. These hot Neptunes provide an opportunity to study atmospheric processes and planetary evolution under conditions different from those in our solar system. Comparative studies between Neptune and these exoplanets enrich our understanding of planetary systems as a whole. In the context of astrobiology, Neptune and its moons, particularly Triton, raise intriguing possibilities. While the planet itself is inhospitable due to extreme temperatures, pressures, and winds, the potential for subsurface oceans on Triton creates a niche environment that could theoretically support life. Such studies expand the scope of astrobiological exploration beyond traditionally Earth-like conditions. The cultural and historical significance of Neptune is equally compelling. Named after the Roman god of the sea, the planet embodies humanity's enduring fascination with the unknown and the vastness of the cosmos. Its discovery through mathematical prediction rather than direct observation symbolizes the power of human intellect and scientific inquiry. In summary, Neptune represents a cornerstone of planetary science, offering profound insights into atmospheric dynamics, magnetic fields, planetary formation, and the outer reaches of our solar system. Its exploration continues to inspire curiosity and innovation, driving the next generation of scientific discovery. The study of Neptune remains a dynamic and expanding field, as astronomers and planetary scientists continue to probe the mysteries of this distant world. With advancements in technology, from Earth-based telescopes to potential future missions, the opportunities to deepen our understanding of Neptune are vast. Each aspect of the planet, from its atmospheric phenomena to its orbital dynamics, provides a rich tapestry of scientific challenges and opportunities. One of the most striking aspects of Neptune's atmosphere is its paradoxical thermal structure. Despite being farther from the Sun than Uranus, Neptune exhibits more intense atmospheric activity and higher temperatures in certain regions. This unexpected phenomenon suggests an internal heat source driving its weather systems. Current models propose that Neptune radiates about 2.6 times more energy than it receives from the Sun. This internal heat, likely resulting from gravitational contraction or residual heat from the planet's formation, contributes to its dynamic climate. Understanding the mechanisms behind this heat release could provide broader insights into planetary thermodynamics. The formation and behavior of storms on Neptune are among the most extreme in the solar system. The Great Dark Spot observed by Voyager 2, though transient, showcased the planet's ability to generate large, stable vortices. These storms are driven by the rapid rotation of the planet, which completes a day in just over 16 hours. The interplay between high-speed winds, varying pressure systems, and the Coriolis effect leads to the formation of cyclonic and anticyclonic systems. Subsequent observations by the Hubble Space Telescope have revealed that new storms frequently form and dissipate, underscoring the planet's volatile and evolving atmospheric dynamics. Neptune's unique atmospheric composition also raises questions about chemical processes in extreme environments. The methane responsible for its blue hue plays a crucial role in photochemical reactions driven by solar ultraviolet radiation. These reactions produce hydrocarbons such as ethane and acetylene, which contribute to the planet's haze layers. The study of these processes is not only relevant to Neptune but also to other planetary atmospheres, including those of Titan and certain exoplanets. Another area of growing interest is the possibility of unusual precipitation on Neptune. Under the extreme pressures and temperatures found deep within the planet's atmosphere, it is hypothesized that carbon atoms could crystallize to form diamonds. These diamonds may rain toward the core, creating a unique geological process that has no earthly equivalent. Laboratory experiments simulating these conditions have shown the feasibility of diamond formation, lending credence to these theories. This diamond rain phenomenon has implications for understanding the interior structures of not only Neptune but also Uranus and similar exoplanets. Triton, Neptune's largest moon, continues to captivate scientists due to its unique characteristics and potential for further exploration. The retrograde orbit of Triton strongly supports the theory that it was captured by Neptune's gravity, likely originating in the Kuiper Belt. This capture would have been a cataclysmic event, disrupting Neptune's original moon system and leading to the formation of the current arrangement. Triton's surface, composed largely of nitrogen ice, exhibits a young and dynamic landscape with relatively few impact craters, indicating ongoing geological activity. One of Triton's most intriguing features is its cryovolcanism. Observations of nitrogen geysers erupting from its surface suggest that subsurface heating is occurring, possibly due to tidal interactions with Neptune. This heating could maintain a subsurface ocean, making Triton a prime candidate for the search for extraterrestrial life. The chemistry of such an ocean, combined with its potential energy sources, could provide a habitable environment, even in the absence of sunlight. Triton also offers a rare opportunity to study the processes that shape icy bodies in the outer solar system. Its cantaloupe terrain, characterized by a network of ridges and depressions, remains poorly understood but could provide clues to the moon's geological history and internal structure. Understanding these features could inform models of other icy moons, such as Europa and Ganymede, and contribute to comparative planetology. Neptune's ring system, though faint, is a subject of considerable interest due to its complexity and dynamic nature. The atom's ring, with its arcs, presents a particularly challenging puzzle. These arcs, dense clumps of material within the ring, defy standard models of ring behavior, which predict uniform distribution. The presence of nearby shepherd moons, such as Galatea, may play a role in maintaining the arc structure, but the precise mechanisms remain unclear. Studying these rings can provide insights into the dynamics of planetary ring systems as a whole, including those of Saturn, Uranus, and Jupiter. Neptune's influence extends beyond its immediate vicinity to the broader structure of the solar system. Its gravitational interactions with the Kuiper Belt shape the orbits of many trans-Neptunian objects, TNOs, including dwarf planets like Pluto. The resonance between Neptune and these objects, particularly the 3:2 resonance with Pluto, highlights the planet's role as a key architect of the outer solar system. Understanding these interactions sheds light on the processes of planetary migration and the early history of the solar system. The search for exoplanets has also placed Neptune in a new context. Many exoplanets discovered to date fall into the Neptune-like category, with masses and sizes similar to Neptune but in vastly different environments. These hot Neptunes orbit close to their stars and experience intense radiation, leading to atmospheric escape and unique chemical processes. Comparing these exoplanets to Neptune provides a valuable framework for understanding the diversity of planetary systems and the factors that influence planetary evolution. Future exploration of Neptune is a priority for planetary science. Proposed missions, such as an orbiter equipped with advanced imaging and spectroscopy instruments, could revolutionize our understanding of the planet and its moons. Such a mission would allow for detailed studies of Neptune's atmosphere, magnetosphere, and interior, as well as in-depth exploration of Triton. Advances in propulsion technology and miniaturization of scientific instruments could make these missions more feasible in the coming decades. In conclusion, Neptune stands as a testament to the richness and complexity of our solar system. Its dynamic atmosphere, unique magnetic field, intriguing moons, and faint rings offer a window into processes that operate on both local and cosmic scales. As our technology and scientific capabilities grow, so too does our potential to uncover the secrets of this distant giant. Neptune's study not only enhances our understanding of planetary science, but also inspires us to look beyond, toward the uncharted territories of the cosmos. Neptune's role in the broader cosmic narrative continues to expand as we deepen our understanding of its dynamics, origins, and implications for planetary science. As one of the most distant planets in the solar system, Neptune offers a glimpse into the conditions of the early solar nebula and the processes that governed planetary formation and evolution. Its complex interplay with the Kuiper Belt and other trans-Neptunian objects also provides critical insights into the outer regions of the solar system, a domain that remains largely uncharted and enigmatic. The study of Neptune's origin is intrinsically tied to models of planetary migration. In the early solar system, it is believed that the gas and ice giants did not form in their current orbits but migrated due to interactions with the protoplanetary disk and with each other. This theory, known as the Nice model, posits that Neptune and Uranus originally formed closer to the Sun and were later pushed outward by gravitational interactions with Jupiter and Saturn. This outward migration had profound effects on the solar system's architecture, scattering smaller bodies into the Kuiper Belt and beyond. Neptune's current position and gravitational influence continue to shape the orbits of these distant objects, including resonant TNOs like Pluto. The interaction between Neptune and its environment extends to its magnetosphere, which remains a fascinating subject of study. Unlike Earth's magnetic field, which is closely aligned with its rotational axis and centered on its core, Neptune's magnetic field is highly tilted and offset from the planet's center. This irregularity is thought to result from the dynamo processes occurring in a shell of conductive fluid, likely a mixture of water, ammonia, and methane ices, rather than in the core itself. The unique structure of Neptune's magnetic field creates complex interactions with the solar wind, leading to auroras and other phenomena that differ significantly from those observed on Earth and other planets. Auroras on Neptune, though faint and difficult to observe, are particularly intriguing. They are caused by charged particles from the solar wind interacting with the planet's magnetic field and upper atmosphere. Unlike the auroras on Earth, which are concentrated near the magnetic poles, Neptune's auroras are more scattered and irregular due to the asymmetry of its magnetic field. Studying these auroras could provide valuable information about the planet's magnetosphere and the composition of its upper atmosphere. The planet's upper atmosphere also presents unique challenges and opportunities for research. Composed primarily of hydrogen, helium, and methane, Neptune's atmosphere undergoes complex processes driven by solar radiation and internal heat. At high altitudes, the interaction between solar ultraviolet radiation and methane leads to the formation of hydrocarbons and hazes, which play a significant role in the planet's overall appearance and energy balance. The dynamics of this hazy layer, including its interactions with lower atmospheric layers and external forces, remain an active area of investigation. One of the most extreme and mysterious aspects of Neptune's atmosphere is the presence of supersonic winds. These winds, which reach speeds of up to 2,100 kilometers per hour, are the fastest recorded in the solar system. The mechanisms driving such high-speed winds are not fully understood but are thought to involve a combination of internal heat, rapid rotation, and complex atmospheric dynamics. The study of these winds not only enhances our understanding of Neptune, but also provides a comparative framework for studying atmospheric dynamics on other planets and even exoplanets with similarly extreme conditions. The planet's deep interior is another frontier of discovery. While direct exploration of Neptune's interior is currently beyond our technological capabilities, theoretical models and laboratory simulations provide valuable insights. The extreme pressures and temperatures within Neptune create conditions that are unlike anything found on Earth. For example, water in Neptune's interior may exist in a superionic state, where hydrogen ions flow freely through a lattice of oxygen atoms, giving the substance both solid and liquid properties. This state of matter has profound implications for understanding the planet's magnetic field and heat transport mechanisms. In addition to superionic water, the possibility of diamond rain remains one of the most fascinating hypotheses about Neptune's interior. Under the immense pressures deep within the planet, carbon atoms in methane molecules could be compressed into diamond crystals, which would then fall toward the core. Laboratory experiments simulating these conditions have supported the plausibility of this process, making Neptune a natural laboratory for studying exotic states of matter. Triton, Neptune's largest moon, continues to be a focal point of interest due to its potential habitability and unique geological features. Triton's retrograde orbit and its likely origin as a captured Kuiper Belt object provide a compelling narrative of the moon's history and its relationship with Neptune. The tidal interactions between Neptune and Triton not only shape the moon's orbit, but also generate internal heat, which could sustain a subsurface ocean beneath its icy crust. This subsurface ocean, if it exists, could be a potential habitat for microbial life, making Triton a key target for astrobiological exploration. The geysers on Triton, first observed during Voyager 2's flyby, are a vivid demonstration of the moon's geological activity. These geysers, which eject nitrogen gas and dust particles into space, are thought to be powered by solar heating of subsurface volatile materials. The study of these geysers and the materials they release could provide valuable information about Triton's subsurface composition and thermal dynamics. Neptune's ring system, though less prominent than Saturn's, is equally intriguing. The faint and dusty nature of Neptune's rings poses significant observational challenges, but their structure and dynamics offer important clues about the planet's history and the processes governing ring systems in general. The discovery of dense arcs within the atom's ring highlights the complexity of these structures and raises questions about their stability and formation. The role of shepherd moons, such as Galatea, in maintaining these arcs is a topic of ongoing research, with implications for understanding ring-moon interactions throughout the solar system. As we look to the future, the exploration of Neptune and its moons remains a high priority for planetary science. Proposed missions, such as orbiters and flybys equipped with advanced instruments, could address many of the unanswered questions about Neptune's atmosphere, magnetosphere, interior, and satellites. These missions would not only expand our knowledge of Neptune, but also provide valuable data for comparative studies of other ice giants and exoplanets. Neptune's significance extends far beyond its role as a planetary body within our solar system. It serves as a bridge between the solar system and the broader universe, offering insights into planetary formation, migration, and dynamics on a cosmic scale. By studying Neptune, we not only learn about our own solar system, but also gain a deeper understanding of the diversity and complexity of planetary systems throughout the galaxy. The mysteries of Neptune continue to inspire and challenge us, driving the quest for knowledge and the exploration of the unknown. The exploration and study of Neptune encapsulate the spirit of scientific curiosity and innovation, as it challenges our understanding of planetary science on every level. From its turbulent atmosphere to its enigmatic interior, Neptune remains a focal point for expanding knowledge about the processes that govern not only our solar system, but also planetary systems across the galaxy. A particularly intriguing area of research involves Neptune's deep interior and the unique states of matter that may exist there. While much of the planet's mass is thought to consist of a mantle of water, ammonia, and methane ices, these materials do not behave in the same way they do on Earth due to the extreme pressures and temperatures inside Neptune. At depths of thousands of kilometers, water may transition into a superionic phase, a state in which it becomes partially solid and partially liquid, with free-flowing hydrogen ions moving through a crystalline oxygen lattice. This exotic form of matter may significantly impact Neptune's magnetic field generation, as it could act as a conductive layer driving the dynamo effect. Understanding this phenomenon is not only crucial for explaining Neptune's tilted and offset magnetic field, but also has broader implications for modeling the interiors of exoplanets with similar compositions. Adding to the enigma of Neptune's interior is the potential for the planet's high pressures to compress methane molecules into diamond. This diamond rain hypothesis has captivated both scientists and the public, as it suggests that Neptune's interior could be studded with vast quantities of these precious stones. Experiments conducted under laboratory conditions that mimic the pressures within Neptune's mantle have demonstrated that methane can indeed break down into carbon, which then crystallizes into diamond. These diamonds could sink through the planet's interior, creating layers or even oceans of diamond crystals. This process could have profound implications for the thermal and compositional evolution of Neptune over billions of years. Neptune's atmosphere, another frontier of research, is a dynamic and chaotic environment, characterized by extreme winds, temperature gradients, and large-scale storms. Unlike the other giant planets, Neptune's winds can reach supersonic speeds, making it the most turbulent atmosphere in the solar system. These winds, which exceed 2,000 kilometers per hour, are driven by a combination of the planet's rapid rotation, internal heat, and complex atmospheric dynamics. One of the enduring mysteries of Neptune's atmosphere is how it maintains such high wind speeds, given the relatively low amount of solar energy it receives due to its distance from the Sun. Theories suggest that the planet's internal heat source plays a significant role, driving convection currents and fueling the intense weather patterns observed. The Great Dark Spot, discovered during Voyager 2's 1989 flyby, exemplifies the dynamic nature of Neptune's atmosphere. This massive anticyclonic storm, comparable in size to Earth, was found to be a transient feature, disappearing within a few years of its discovery. Subsequent observations with the Hubble Space Telescope have revealed other dark spots forming and dissipating over time, indicating that Neptune's atmosphere is in a constant state of flux. These features provide valuable opportunities to study storm formation and evolution under extreme conditions, offering parallels to atmospheric phenomena on other planets and even Earth. One of the most surprising aspects of Neptune's atmospheric chemistry is the presence of hydrocarbons and other complex molecules formed through photochemical reactions. When methane in Neptune's upper atmosphere is exposed to ultraviolet radiation from the Sun, it breaks down and recombines into more complex hydrocarbons such as ethane, acetylene, and propane. These molecules contribute to the planet's haze layers, which in turn affect its energy balance and thermal structure. The detailed study of these processes has implications for understanding not only Neptune but also other planetary atmospheres, including those of exoplanets with methane-rich compositions. Neptune's connection to the broader solar system is exemplified by its gravitational interactions with the Kuiper Belt, a region of icy bodies and dwarf planets beyond its orbit. Neptune's migration early in the solar system's history played a critical role in shaping the orbits of Kuiper Belt objects, KBOs, and creating the resonant structures observed today. For example, Pluto and other Plutinos are in a 3:2 resonance with Neptune, meaning they complete 3 orbits of the Sun for every 2 orbits of Neptune. These resonances highlight the planet's profound influence on the architecture of the outer solar system. The study of Neptune's moons, particularly Triton, continues to reveal new insights into the dynamics of satellite systems. Triton's retrograde orbit, highly unusual for a large moon, strongly suggests that it was captured by Neptune rather than forming alongside the planet. This capture event would have been a violent process, potentially disrupting any pre-existing moons and altering Neptune's early satellite system. Triton's current orbit is slowly decaying due to tidal interactions with Neptune, and in billions of years, it may either collide with the planet or be torn apart to form a new ring system. Triton's surface and geology are of immense scientific interest, as they provide evidence of active processes rarely seen elsewhere in the solar system. The moon's nitrogen geysers, first observed by Voyager 2, are powered by sublimation, where sunlight heats subsurface nitrogen ice, causing it to vaporize and erupt through surface vents. These geysers deposit dark material onto Triton's surface, creating streaks that reveal the direction of winds in the thin atmosphere. The presence of active geysers suggests that Triton is not a geologically dead world, but one with ongoing processes that could include cryovolcanism and tectonic activity. The potential for a subsurface ocean on Triton is another tantalizing possibility. If such an ocean exists, it would be kept liquid by a combination of tidal heating and the insulating properties of the moon's icy crust. This ocean could harbor conditions suitable for microbial life, making Triton a prime target for astrobiological exploration. The chemistry of Triton's ice, combined with the energy provided by tidal forces, creates a unique environment that may parallel other ocean worlds in the solar system, such as Europa and Enceladus. Neptune's ring system, though faint and less prominent than Saturn's, is an area of ongoing study. Composed primarily of dark, dusty material, Neptune's rings are believed to be relatively young and dynamic. The Adam's ring, in particular, is notable for its arcs, denser regions within the ring that remain mysteriously stable despite the forces that should cause them to disperse. Theories about the arc stability often involve the influence of nearby shepherd moons, such as Galatea, whose gravitational interactions may help maintain the ring structure. Studying these rings provides valuable insights into the processes governing ring dynamics and evolution across the solar system. As technological advancements continue to enhance our capabilities, the future exploration of Neptune holds immense promise. Proposed missions, such as a Neptune orbiter equipped with high-resolution imaging and spectroscopy instruments, could revolutionize our understanding of the planet and its moons. These missions would allow for in-depth studies of Neptune's atmosphere, magnetosphere, and interior, as well as detailed exploration of Triton's geology and potential habitability. With the possibility of sending atmospheric probes to directly sample Neptune's composition, such missions could address fundamental questions about the planet's formation and evolution. Neptune also serves as a natural laboratory for comparative planetology, particularly in the context of exoplanet studies. Many exoplanets discovered to date fall into the Neptune-like category, with similar sizes and compositions but often in vastly different environments. By studying Neptune in detail, scientists can develop models to better understand these distant worlds, including the processes that govern their atmospheres, interiors, and magnetic fields. In the grander scheme, Neptune represents humanity's enduring quest to explore and understand the cosmos. As one of the most distant planets in the solar system, it challenges us to push the boundaries of technology and knowledge. Each discovery about Neptune not only enriches our understanding of the solar system, but also inspires us to continue exploring the unknown, seeking answers to the profound questions about our place in the universe. Neptune's continued study holds an unparalleled promise for unlocking secrets of both our solar system and planetary science as a whole. This ice giant, despite its distance and relative observational challenges,